The topics of permutations and combinations are generally considered to be topics for a course in combinatorics, but number theory has a way of taking ideas from other areas and using them productively. We will begin by building some basic intuition about making selections. Suppose that you are trying to make simple bagged lunches at a school. All the lunches come with milk and a cookie for dessert. But the students can have their choice of a sandwich and their choice of a fruit. The sandwich options are peanut butter and jelly, turkey, or ham, and the fruit options are an apple or an orange. How many different lunches can be made? We will ignore the milk and cookie because both of those are standard in every lunch. The variety only comes from picking the sandwich and picking the fruit. We can represent the choice of sandwich in the horizontal direction and the choice of fruit in the vertical direction. What we can see from here is that we can make a grid that represents all the possibilities, and that the number of options is the product of the number of options for each choice. In this case, there are 6 different lunch options. If we expanded the selection to include options for dessert, say a cookie or a brownie, we would end up with 2 copies of this grid, one for each dessert choice. Notice how this still corresponds to multiplying by the number of options for each choice. If you wanted, you can try to imagine stacking the grids on top of each other to create a 3-dimensional grid, but that type of generalization runs into problems if you have a 4th option, such as choosing between milk and juice. When we have many options, we tend to use a tree for visualization. We simply list all the items vertically in groups and then connect them with lines. Each pathway represents a different meal. This is helpful when thinking about this as a process, but it doesn't provide as much intuition about why we would multiply the numbers at each step. This idea is formalized in the book as the general combinatorial principle. The general combinatorial principle. If an element alpha can be chosen from a prescribed set S in m different ways, and if a second element beta can be chosen from a prescribed set T in n different ways, then the ordered pair alpha beta can be chosen in m times n different ways. Returning to the first example with only 2 options, the set S is the list of sandwich options and the set T is the set of fruit options. As mentioned, this principle can be generalized to any number of selections. It's important here that the number of choices at each step is independent of the previous choices. This principle would not work if selecting a turkey sandwich meant that you also had to have an apple. The next combinatorial principle we will need is an R permutation. Definition: an R permutation of the set S of n objects is an ordered selection of R distinct elements from S. For example, let S be the set containing A, B, C, and D, and let's try to count all the possible 3 permutations. That is, we're looking for an ordered collection containing 3 non-repeating symbols from the set S. For first choice, we have 4 objects to choose from. For the second choice, we can't choose the first object again, so we have only 3 objects to choose from. Notice that even though the specific options may be different, the number of options to choose from will always be 3. For the third choice, we only have 2 options remaining. By the general combinatorial principle, since there were 4 options, then 3 options, then 2 options, we multiply those numbers together to get 24 possible 3 permutations. And you can see them all listed here. The next theorem provides a formula for the number of R permutations of a set of n objects. We read this symbol as n permute R. The proof is nothing more than thinking through the number of choices at each step and applying the general combinatorial principle. For the first choice, there are n options. For the second choice, there are n-1 options. For the third choice, there are n-2 options. And the pattern continues all the way down through the rth choice. At this point, there are n minus r plus 1 options. Using the general combinatorial principle, we multiply these numbers together to get the desired result. As a quick notational note, we define n factorial to be the product of the first n natural numbers. For example, 4 factorial equals 4 times 3 times 2 times 1, which is 24. For convenience, we will define 0 factorial to be 1. Definition: an R combination of a set S of n objects is a subset of S containing R elements. The difference between combinations and permutations is that the order does not matter for combinations. If we look at the 3 permutations from before, we condense the list into 3 combinations by just matching up the ones that use the same symbols. From this, we can see that there will never be more R combinations than R permutations, since one R combination can be associated with many R permutations. In fact, this idea is applied directly into the next theorem, which provides a formula for computing the number of R combinations from a set S. This symbol is read n choose R. For each of the n choose r different r combinations, we can generate r permute r different r permutations. Therefore, we must have this equation. Upon rearranging this and substituting the formula from theorem 3-1, we get the desired result. The symbols n choose r are also known as the binomial coefficients and are extremely important in combinatorics. But that's a conversation for another class, so we'll end this video here.
Thank you for watching this video. I'm currently dabbling with the idea of creating more videos like these for my classes, and I welcome constructive comments that might help me make better videos in the future.